Okay, hi. I'm Axel, and I'm loud on the internet. I want to talk to you about a complication we encountered with designing generics. And just as a side note, some people get annoyed when mathematicians use we all the time. If you're one of these people, just pretend that I talk about my favorite sports team, right? Like, we won the championship, even though I didn't do anything. I just use it by habit. So the specific feature that I'm talking about has to do with union elements. So if you've been using generics, you probably know that you can specify constraints. And one way to specify these constraints is using just a list of types where you say, my type parameter has to be one of these specific types. And the most common way to use that is to allow your generic function to use operators, right? Like if every type in this list supports plus, you can use plus in your generic function. But another thing that would be nice to use this for is to actually use fallback methods instead of operators. So in this example, we have a function stringify that can take anything that either implements fimp.stringer or has underlying type string. And this function will then just do a type assertion, is this a fimp.stringer, and if so, it will stringify using the string method, and otherwise it will use reflect to unpack the string, right? And so this would be a very nice thing to do. But unfortunately, if we try to do that, the compiler will just tell us no. You cannot use fimp.stringer in a union because fimp.stringer has methods. And this is because the spec actually contains an exception for this specific problem. It says a union with more than one term cannot contain the predeclared identified comparable or interfaces that specify methods or embed comparable or interfaces that specify methods. So basically, the spec says, no, this specific thing, nice as it would be, you can't have that. And so the obvious question is, why, right? Like, if this is a nice feature, this example, this stringish example, is from the design doc for generics. We obviously expect it to be able to do this. So why do we forbid it? And to understand that, we have to do a little bit of theory, and this is where it's going to be fun, for me at least. So you might have heard about the P versus NP problem. To explain a bit what that's about is there's basically, we are talking about two specific kinds of computational problems here. One class is P. P is the class of problems that can be efficiently solved. Like a simple example of that is multiplying two integers. If I give you two integers, you can write down an algorithm that very efficiently multiplies them and gives you the product of them, right? And then there's a class NP. And NP is the class of problems that can be efficiently verified, meaning that if I give you a solution, you can write an algorithm that efficiently checks that this solution is correct. Again, an example is if I give you an integer n and two prime numbers p and q, and I tell you these two prime numbers multiply to n. You can very efficiently verify that by just multiplying them together, comparing them to n, everything's fine, right? And P versus NP is the question is, are there problems which are efficiently verifiable but not efficiently solvable? And this is an open problem. We don't actually know whether that's the case. But we generally do assume that this is the case. We generally assume that there are such problems. And again, one intuitive example is it is easy to verify whether two primes multiply to an integer, but if I would just give you the integer and tell you, please give me the prime factors of this number, probably the best thing you can do is go through all possible prime numbers and try to divide them, divide n by them, and if so, you have found them, but like that takes a lot of time, right? So at best, as we know, this is a good candidate for an example that is in NP but not in P. But if we don't actually know, if we don't actually know that there are such problems, like how does it help us, right? How can we actually deal with that in practice? How can we use that, apply that to practical problems? And the answer to that is that there's a class of problems that are called NP-complete or NP-hard. One of these is the Boolean satisfiability problem. So the Boolean satisfiability problem means I give you a Boolean formula, so a function, basically a function that takes only Boolean arguments and returns a Boolean. and I ask you, is there a set of arguments to this function that will make the function evaluate to true? That is the Boolean satisfiability problem. Like, is this function satisfiable? For example, I have like a random formula here. And if you actually put in true, true, false, you will notice, no, the function is false. But if you put in false, true, false, it will actually evaluate to true. Like, so in this particular case, the answer is yes, this function is satisfiable, and a satisfying assignment is false, true, false, right? And we have proven in a way that I certainly don't understand and that we don't have to care about right now, but we have proven that every problem in NP can be reduced to SAT, right? So we have proven that this particular problem, turns out, is at least as hard as any other problem in NP. So if we can solve SAT, we can solve any problem in NP. And given that we assume that there are problems in NP which are not efficiently solvable, we assume that there is actually just no efficient way to solve SAT. So if we care about these things, if we care about our computers being efficient, our algorithms being efficient, we have to assume that if we have to solve SAT, we should just give up, maybe. Or at least we're going to have a bad time. So how does this apply to Go, right? How, like, once we understood all this theory, how can we apply that to Go? It turns out when we compile Go programs, the compiler also has to solve some decision problems. For example, it has to answer the question, given a constraint, C1, does a given type satisfy this constraint, right? And this is important if we have a generic function, for example, G in this case, and we call it with a concrete type. Then the compiler actually has to check, does this type actually satisfy this constraint? Logic, right? But another question the compiler has to answer is, if a type satisfies C1, one constraint, does it also satisfy C2, another constraint? So does satisfying one constraint imply another constraint? And this is important if we have a generic function that has constraint C1 and that calls another function that has constraint C2, then the compiler actually has to make sure that this call is safe, right? It has to check, does every type that satisfies C1 also satisfy C2? And so my claim is that deciding this second problem is actually one of these very, very hard problems. It is co-NP hard. So so far I've talked about NP complete. Now I am saying co-NP complete. The co is a bit of a technicality. The co comes from the fact that we actually invert the answer, right? Like, where with NP complete, the yes answer would have to be easily verifiable. With a co-NP complete problem, the no answer is easily verifiable, right? With the satisfiability problem, a yes answer takes the form of a satisfying assignment. That is very easy to check. With our type checking problem, the answer is a type that would satisfy C1 but does not satisfy C2, which is then easy to check, but that is a no answer. In this case, like, the implication is false. But in terms of, like, difficulty to solve the problem, both are the same, right? You just answer yes instead of no, or no instead of yes, but you have to solve exactly the same, like, level of complex problems. Okay, so how do we prove this claim that this particular problem is co-NP hard? Oh, sorry, just to be clear, I'm using the word NP hard and NP complete interchangeably. They are not technically speaking interchangeably, but for our purposes, they are. So how do we prove that? The answer is by doing a reduction proof. A reduction proof means that basically you give me an instance of a satisfiability problem, and you give me an oracle that solves the problem we are interested in, like this type problem. So you give me a Go compiler that can solve this type problem. And then I will use this oracle, this compiler, to solve the satisfiability problem. And by doing that, I have proven that if I can solve the type problem, I can solve the satisfiability problem by just calling my compiler with the right Go program. So we construct a Go program that solves our satisfiability problem. And to do that, first we define two interfaces for every variable in our formula. One interface is x, that it just has the method x. And this interface represents basically the variable x is true in our hypothetical assignment. And we define not x, which is, just has the method not x, and that represents x is false in our particular assignment. And if we do that, we can just take our formula and translate it one-to-one into a Go interface. by just taking, replacing every OR operator, every logical OR, with a union, every negation with like the corresponding NOT interface, and every AND in the formula by just doing a line break or a semicolon to embed another interface to say it has to satisfy all of these. And with this translation, like intuitively, any type satisfying formula should give us an assignment of variables that will make the formula come true. Like if a type satisfies formula with these methods, it has to give us an assignment to make the formula true. But this is not quite correct yet. Because it turns out a type can have neither of x or not x, right? Like a type is not forced to actually have any of these methods, which is not true for Booleans. Like a bool can't be neither true nor false, right? The other problem is a type can, of course, have both x and not x. There's nothing preventing that. And again, with bools, that is not true, right? Like a bool can't be both true and false. And so we do have to do a little bit of extra work to solve these two problems. And the way we do that is by putting more interfaces into our program. The first interface I called at least one. And this is an interface, a type satisfying this interface means the type is guaranteed to have for every variable at least one of the x or not x methods. And we do that by just writing down x or not x, like x union not x, and y union not y, and so on for all the variables. And now every type satisfying at least one will have for every variable at least one of the methods. So we solved our first problem with that. The second problem we solved similarly by defining an interface that represents a type having both for at least one of these variables. So again, we define a bunch of interfaces. The both x interface means a type has both an x and a not x method. The both y has both a y and a not y, and so on. And then we define the both interface, which just says, which is just a union of both x, both y, and both z, and so on. And so any type satisfying the both interface will have for at least one of the variables both assigned, right? So to get a valid assignment to our formula, our type would have to implement the formula interface. It has to implement the at least one interface to make sure that it has at least one of the methods for every variable. And it must not implement the both interface to guarantee that it does not have both set for any of these variables. And so this now lets us finish the proof, right? We just write the program where we have a generic function f, which has a type parameter that is constrained on formula and at least one. And the function f calls g. G has a type parameter where the type parameter is constrained on the interface both. And now this is where the co-NP stuff comes in. We say if our compiler, is supposed to accept this program if and only if formula and at least one implies both. Like this is how we defined our type problem. And so we say if the compiler answers no to that by doing some, like, if you're a mathematician, trivial logical equivalencies, that actually turns out to be equivalent to formula being true and at least one being true and both being not true. Again, I acknowledge that this is maybe a bit technical for the general audience, but I will also publish a blog post with all the details, and you can like sit down and actually look it up. But for now, like, just trust me, this conversion is sound. This transformation is sound. All right. And so with this, actually, we finished our proof. Like my claim, I have proven my claim, or I claim that I have proven my claim. That actually implementing a type checker, if we were to just allow methods in unions, if we were to implement a type checker that is precise, that would actually be just an NP complete problem or a co-NP complete problem. And so if we want to do that, we are going to have a bad time. But that's not satisfying. Pun intended, because we want to use this feature, right? Like this stringify example is a very useful thing, and it's very frustrating right now that we are actually not able to write a generic function that can work both with built-in types and use operators, and with like composite types that use a method, right? And so we do want to find some way to go forward, and for that we will have to find some compromise. The first way we could actually decide to go forward is to just ignore the problem, right? We just say, so what? We have to solve an NP-hard problem. It's not like they are unsolvable. It's just they take a long time to solve. And this is a bit like, this may sound a bit wild that I just like told you very extensively in many words how hard these problems are to solve. And now I say we can just ignore it, right? And I don't find this solution particularly satisfying. I don't like it, but it is certainly a practical way to just deal with it. To just say, well, the compiler will just have a SAT solver. It will just try, and if it can't, it will just, I don't know, give up after 5 seconds or whatever. And it turns out actually C++ has this problem. Like C++ concepts, in at least one instance, have to check whether this implication is true for constraints. And it turns out C++ just did this, right? Like this C++ spec just basically says, well, your compiler needs a SAT solver to prove whether one constraint implies another, and you can write a C++ program that just takes functionally infinite time to solve, like to compile. And yes, you can actually make compilers blow up. I tried. It works. So I want to emphasize, like, I don't like it, but this would be a way we could actually like approach this. Another way to approach this is, well, the way I presented to you the satisfiability problem was the most general way. Like, you have a very general Boolean formula, and that is actually NP-complete. But it turns out there are subproblems of the satisfiability problem that are actually easy to solve. And one of them is if we know that our formulas are given in disjunctive normal form. Again, I apologize for not like explaining more what that means. I don't have the time. But just basically this means that you have like just a set of terms that are combined with ORs, where each term is just a list of ANDs. Anyway, it turns out what is important is it turns out that if we already know how to solve SAT for our current interfaces, basically. Like if we don't allow methods at all, then we already know how to solve SAT. And so it turns out if we were to allow methods in interfaces, but only one level deep, we say our interfaces are allowed to have methods in a union, but then they can only have one union, and this union can have such interfaces, but all the interfaces in the union must be interfaces we currently allow. Then the resulting constraint would actually be in disjunctive normal form. And then we could actually just solve this. We could actually just write down an efficient algorithm to solve this, right? And I'm not quite sure, like this is just one example of a way we could structurally constrain the interface language while still allowing us to write many useful programs. I'm not sure this is like the right one we would want to use because it is also kind of hard to explain. But there might be others. There are many others, right? There is a huge space of possible satisfiability problems. Some of them are NP-complete, some of them are not. And we could try to just put on artificial constraints that would allow us to constrain, like to limit the expressiveness to one of these solvable subsets. Another way to address this would be to make the type checker more conservative. So one thing I emphasized is our type checker is supposed to compile the program if and only if the implication is true. But we could also just say the compiler is allowed to reject programs that might be safe, but where the compiler can't prove that they are safe, right? Like we could write an algorithm that would just, for many cases, be able to decide that the implication is actually true. But in some cases where it is true, would just fail to prove it and reject the program and say, please restate your program in a way that I can actually understand. And this is actually basically what static typing is all about. Like static typing is all about taking a program that might be valid, but where the compiler is not sure whether it's valid, and proving to the compiler that it's valid by annotating it with types, right? But if we do this, again, we have to be very clear what algorithms we use and what kinds of programs we actually want to be able to write and what not. And this is actually, again, not a particularly trivial problem. Like in this example, we have a Marshall function which is constrained on stringish or bool or constraint.integer. And like obviously we would want to, if we have a function f which is constrained on stringish, we want that to be able to call Marshall, right? Because stringish is a constraint that is in this list of types, right? But again, it's not the same constraint. It's just the constraint we have, it happens to also be in this list of types. And we have to think about the fact that there's actually nothing forcing us to even write fim.stringer, right? Like fim.stringer is also just a shortcut for writing a string method with a string return. But what's even worse, we could also imagine this function g, which is constrained on string and fim.stringer. And we probably also want to allow that, because if the type parameter is a string, then it has underlying type string, and so it satisfies stringish, and so it should actually be able to call Marshall. And if it's implementing fimp.stringer, it also implements stringish, and so on. But in this case, like, the compiler can't even just do a strict, like, A is a subset of B, right? It actually has to do more inference on the actual structure of the constraints. And there are more complicated examples I could give. Like, there are examples where both interfaces are actually the same. Like, they describe the same types, but to the compiler, they look like completely different. But again, this would be a simple thing to do. Like, this is a simple thing to say we want to do, but the devil is in the detail. We actually have to, like, sit down and actually write out what is the specific algorithm the compiler uses to check whether one call is allowed or not. And probably this would go hand in hand with the previous thing. Like, probably we would restrict our interface expressiveness to a level that we can write such an algorithm, and vice versa. One more thing we should keep in mind, that we will probably want to extend our generics design at some point. For example, there is a proposal by Roch Pepe that I really like, which is to allow type switches on type parameters. And the way this is proposed to work is that we introduce a syntax like switch type T, and then you can have cases, and each case also mentions a constraint. And then if our type parameter satisfies this extra constraint in the case block, we would be able to, in this block, use the type parameter as if it was constrained by both, right? And this would be again very, very useful, because, for example, we can write our stringify function without needing reflect, because now we can just do basically a type assertion on the type parameter to is the underlying type string. And then we know that our type parameter can be converted to string, because in the case block, it is constrained by stringish intersected with underlying type string, which is just underlying type string. But this is a nice proposal. And if we want to do that, we should actually make sure that our, like, restriction of the interface constraint language or whatever is compatible with this, right? Because this allows us to implicitly create new constraints in a type switch. And so we need to make sure that when you do that, the newly constructed implicit constraints are still compatible with our structure, right? And with my example of the disjunctive normal form, this would no longer be the case, right? Because or at least we would have to take care that it is the case, and we would have to take extra care on what programs are allowed, because this intersection is now it's no longer just a single list of unions, because now it is actually an intersection of two single lists of unions, which is different. And so now I hope I actually apparently spoke very fast. I hope I convinced you first that if we were to just, like, if you just think, like, why is this not allowed? Just allow it. Can't be that hard. That would at least require us to put a SAT solver into the Go compiler, at the very least. But I also hope that I showed to you that this kind of, like, this argument also gives us a little bit of hope, or at least a little bit of, like, some specific levers we can use to maybe get some of the power back, by either, like, putting structural restrictions on the interfaces that would allow us to express some programs we like, or by just making or by making the type checker a bit conservative. But again, we will have to talk about that. Like, this is not something that we can just do. There's a lot of subtlety involved, and it will require very careful design work no matter what, because there are a lot of rough edges, and it's actually, like, very, very easy to accidentally putting in an NP-complete problem. Like, when we first proposed generics this way, we didn't know. Like, it took us a while to actually figure out that what we did would have made the language NP-complete, or would have made tab checking NP-complete, and putting thus in this restriction that methods can't be in. Like, this was a last-minute addition to the generics design based on this kind of argument. But yeah, I hope at least when the discussion comes up, I can now point to this talk and say, here is an argument to why this is not as simple as you think, but also this is how we can go forward still. So yeah, thank you. You can ask questions on Slack. You can also reach me on Mastodon. I'm mirovius@cast.social. And also, I have a blog, and on this blog, I will also, in the next few days, publish a post that contains all the details in far more, like, hopefully more understandable, with all the examples that you can then hopefully walk through and recap, like, I don't know, understand better what I said. Thanks.